Did you know that black holes will eventually dominate our universe? Imagine a world where stars fade and die, and black holes are all left everywhere. I'm not saying this, but Stephen Hawking did in 1974. Is this our fate? Join me on this journey as I unveil the shocking reality of black holes. Undoubtedly, you've heard of the standard definition. A black hole is a region in space where matter adjusts into a tiny space, inducing a strong gravitational pull. Nothing, not even light, can escape. As there's no light, we can't see black holes. Curious observers may ask, why can't light escape? The simple answer is that the speed of light is lesser than escape velocity. While their concept is exceptional, black holes are really simple. They consist of two main components, the event horizon and singularity. The event horizon marks the limit of a black hole. The interesting fact about this component is that the escape velocity remains equal to the speed of light here. Singularity is a point that's infinitely dense and small. Here, all mass of the black hole is concentrated. The laws of physics, we are all told, break here. But don't forget that exceptions exist. Now, let's go to the question we've all been waiting for. What is the black hole era? However, let's begin with what's happening in the current era before moving on to the shocking events in the far future. So, we're in the middle of the stelliferous era, which means having or abounding with stars. During this era, the nuclear fusion of ordinary stars produces most of the energy in the universe. It's expected to last from about 1 million to 100 trillion years after the Big Bang. Now, imagine the following period, the universe without stars. This era is called the degenerate era. All stars will exhaust their fuel and go dark. The degenerate era is expected to last between 1 quadrillion and 1 duodecillion years after the Big Bang. The universe will have stellar remnants such as brown dwarfs, white dwarfs, black holes and neutron stars. The environment will continue to darken and cool over time. Eventually, life will likely come to an end. Finally, we get the black hole era. This period will likely last from about 10 duodecillion to 1 googol years after the Big Bang. Nothing will linger in the universe except black holes. Even heat and light will lose their intensity. There will be nothing except black holes, which will become larger like monsters. Dense and massive black holes will produce considerable distortions in the fabric of space-time. But how? The theory of general relativity says that gravity influences all measurements of space and time near the black hole. When massive objects gain speed, they create gravitational waves, ripples in the fabric of space-time. The effects of some ripples are detectable. As a massive object, a black hole tends to bend and distort light from more distant objects. Amazingly, this gravitational influence will only grow as black holes attack the lingering remnants of matter. Undoubtedly, black holes are mortal based on their evaporation process. Here comes the concept of Hawking radiation. Before we move on, we must understand the laws of black hole mechanism. The Canadian theoretical physicist Don N. Page presented the scenario in his 2005 publication Hawking Radiation and the Black Hole Thermodynamics. His article draws attention to the thermal behaviour of black holes. These astronomical objects are observed as the most perfectly thermal objects in our universe. However, their behaviour isn't yet fully defined. But how can we say that black holes have thermal properties? So, the strong hints come from their macroscopic properties, considered in the laws of the black hole mechanism, comparable to the thermodynamics concepts. Stephen Hawking is famous for his work on black holes. According to his work, black holes release radiation in the form of thermal energy, which we call Hawking radiation. Hawking radiation is observed near the event horizon, a point of no return. Quantum theory says that the empty space isn't actually empty. Instead, it's full of virtual particles and antiparticles that briefly wink in and out of existence. Generally, the particles annihilate each other, making no effect. However, things are different near the event horizon. One of the particles escapes to infinity, while the other falls into the black hole. So the black hole loses some mass and energy, and the escaping particle turns into real radiation that's very slow and weak. For a typical black hole, the temperature of the radiation is about 10 millionth of a degree above absolute zero, and the rate of mass loss is about 1 billionth of a billionth of a gram per second. So you can estimate how long black holes evaporate completely. Once they evaporate, the black hole era ends. Remember that the smaller the black hole's mass, the higher the rate of Hawking radiation. Finally, the black hole appears so small and hot that it bursts a huge amount of radiation and explodes. Here we can announce the black hole's death. The death of black holes raises many questions, such as, what about the information stored in them? Due to its thermal nature, the radiation can't hold information. So, when black holes evaporate, it eliminates the memory of the stars that formed it. Now, recall the laws of quantum mechanics, according to which information never gets destroyed, and the final product reveals clues about its previous existence. This problem has caused troubles and is thus called the Hawking information paradox. What do you think? Whether the information about stars is retained or not? Let's share your thoughts in the comments before I explain the answer. The researchers claimed that black holes weren't bald, but had a quantum hair. Now you can say that the Hawking radiation carries information, but how can scientists see this information? Well, they can't see the information with their instruments. The radiation is weak enough to be undetectable. I share one analysis, but there are controversies regarding the baldness of black holes. Let me share something very interesting. What if a black hole touches our solar system? So you can better imagine the time when black holes will dominate our universe. The gravitational effect of a black hole comes first into the mind, depending on its mass. Robert McNeice from Loyola University, Chicago, claimed that black holes are much more massive than the Sun. We know the Sun's gravity affects different phenomena in our solar system, so black holes that are more massive than the Sun would have considerable effects. Some experts even consider Planet 9, a hypothetical planet, to be a baby black hole with a mass comparable to that of a primordial black hole. Primordial black holes were believed to emerge just after the Big Bang, so they aren't expected to spell disasters in our solar system. On the other hand, if a larger black hole invades our solar system, something dangerous is expected. It depends on the speed of the black hole. Imagine this black hole disturbing comets and asteroids and eventually heading towards Earth. How dangerous it seems. Black holes can even change our seasons. Imagine yourself being in an ice age or a region hot enough to cause death. Well, black holes have always been observed as monsters. Nothing seems positive from their side. Imagine falling into a stellar-sized black hole. You turn into a human spaghetti as the gravity field is so strong. You'd be stretched more and more as you get closer to the black hole. Stephen Hawking first described this phenomenon in his book, A Brief History of Time. It's called spaghettification. But guys, don't worry. Robert McNeice stated that our universe has a very small number of black holes, so the chance of one disrupting our solar system, even a single time, is much less. Yes, but the idea is quite interesting for science fiction movie writers. Well, it was an assumption, but black holes will really dominate our universe after a long time. Are you curious to know what happens after their era? Well, there will be the dark era, in which only a few subatomic particles and dark matter will wander in our universe. There will be continuous expansion due to cooling effects, and eventually the remains will stay quite far apart. So subatomic particles will observe incredibly rare interactions. However, occasional collisions are still expected. Many experts believe that our universe will be cool enough to have a big freeze, eliminating heat from everywhere. Eventually, there will be total disorder, or we can say maximum entropy, and our universe will experience inevitable heat death. There's a detailed video on the concept of inevitable heat death on my channel. Don't forget to check that out. So guys, the future of our universe seems dark, but science creates possibilities. There may exist billions of universes out there, and scientists have observed the way to tunnel from one to the other. The heat death may not end everything. As science pushes its boundaries, there will be a map to follow in the future. Let's recall the important points from today's video. So, we're staying in the middle of the Stellariferous era. Then, we enter the Degenerate era, where stars exhaust their fuel and go dark. Finally, there's the Black Hole era, where black holes dominate our universe. They release Hawking radiation, which is observed at the event horizon of black holes. There's a controversy about whether black holes can store information or not. Dense and massive black holes will produce considerable distortions in the fabric of space-time. Black holes evaporate slowly. When all evaporate, the black hole era will end. We also discussed the baby black hole while learning the behaviour of black holes towards our solar system. After the black hole era, the universe will undergo heat death. And so there you have it. The mysteries of the universe are so interesting to explore. Keep on learning. One day, You might find a way to avoid the inevitable heat death. I hope you enjoyed the video. I'm excited to read your thoughts in the comments below.